Hey, this is Leach with Simpson Math, and today we're talking about sampling distributions and the central limit theorem. To your left, you should see an applet. I'll have the link to this applet in the description below. At the top of the applet, we have a normal model curve. In a moment, I will take some random samples from this curve, and we'll then calculate the mean and start graphing that. So let's see what happens. I'm going to tap this animated button, and it will drop down from my it will drop down from my population 5 randomly selected values, and that's what's my sample data. From that, those 5 data values got averaged, and then I graphed the mean. So that one blue box is the mean of those 5 data values. I can do it again. There's another brand new random sample of 5 data values, and then from those 5 data values, I created a mean and dropped it down in my distribution below, that third distribution. All right, let's do it again. 1, 2, 3, 4, 5, mean. Another one, 1, 2, 3, 4, 5, mean. One more, 1, 2, 3, 4, 5, mean. So this third distribution is creating what we call a sampling distribution. Emphasis on that bling, emphasis on that ing. A sampling distribution is a distribution that is made up of statistics. Here we are using randomness in a simulation to create these sampling distributions. But in theory, what this sampling distribution, that third distribution is if I was to be able to take every single possible combination from the population in my sample and graph and find the mean of every single one of those possible samples and graph those, that would produce this sampling distribution. We're doing a more simulated approach where I'm just simulating the sampling distribution, and I'm going to be actually doing this hundreds of thousands of times. So I can speed this up. Instead of doing this at one at a time, I'm going to do them in chunks of 5. If you look to the left, you'll see that I've done this 5 times. It says reps 5. I have a mean of 0, which is actually an error, and a median of 17, and standard deviation of 0. I feel like I should refresh this. This is not working right. All right, welcome back. I investigated the problem, and for some reason, when I do the one at a time animations, it doesn't calculate the mean and standard deviation with those. For some reason, I don't know why, but so I just did 5 new ones, and it is doing my calculations. All right, so now I'm going to press the 5 button instead of the animated button. What the 5 button is going to do is, instead of doing 1 at a time, which took a moment, we're going to do 5 at a time. So it's going to speed it up. So I'm going to press the 5. And there, all of a sudden, all at once, I just did 5 values. So I sampled 5 data values, found a mean. 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 Lastly, 5 data values, found a mean. All right, I can do that again. So now there's another 5. There's another 5. There's another 5. And you see, as I'm doing these 5s, it's this distribution, the sampling distribution, is starting to take shape. Notice it's not very likely that I get a number pretty close to the top or the bottom. It's actually pretty common that I get a number that it grows and adds to the middle there. And it's starting to look somewhat unimodal, maybe even, dare I say, symmetric. And potentially, as I just passed 300, it's getting almost more and more normal. All right, I'm going to stop when we get to 500. All right, there. So I've just taken 500 samples of sample size 5, and from each of those sample size 5s, I calculated a mean. And so here's my graph of those 500 means. Every single one of those blue dots on that graph is a mean, is an X bar. At the top of my graph, I have X's. In the sample data, like if I do my sample data, 1, 2, 3, 4, 5, those are X's. From that, I then calculate a mean and put it on the blue graph. All right, now I can speed this up, and let's do this 10,000 times. Bam. So now I've done this a total of 70,500. If I'm in the mood, I can even do a few 100,000s. So I've just done this over like 1.1 million times. 1.1 million times. And notice it's quite normal. How about that? Right? It's pretty much it's a normal distribution. It's just smaller and skinnier. You might be like thinking to yourself, okay, Mr. Leach, this doesn't seem too shocking. Okay. Um, but let's write down something. I want to on this table document my standard deviation. All right. So in my over I just did it a few more times over 2 million times. My standard deviation is 2.24. So when I did sample size 5, I had a standard deviation of 2.24. All right, I'm going to backtrack and do sample size 2. So again, sample size 2, I do 1, 2, there's a mean. 1, 2, there's a mean. 1, 2, there's a mean. All right, do you see what's happening? Get my sample, produce a mean. I'm interested in that blue graph. Okay, let's speed this up. Jumping in chunks of 5. And notice when I do this, already you can tell that it's a little bit wider than what we saw a second ago. But it's doing a similar thing where it's starting to feel like it's approaching a unimodal distribution, potentially maybe even a symmetric distribution, and maybe even a bell shape. And actually, I'm going to speed this up. Let me do this 10,000 times, now 100,000 times. So there I've done it over 1,000,000 times now. And I can tap this fit normal. It actually does a pretty good job of fitting this normal distribution. There is a little slightly known error in this applet that it fits the normal slightly a bit too far to the right. Fits it over the right of the bins instead of centered. But that's something they're working to fix. So, all right, let's write down our standard deviation from this. So we get our standard deviation is 3.54. And we should notice that that standard deviation, I'm getting that from that red that's to the left. It's red SD is 3.54. Notice that it, as my when I went from sample size 5 down to 2, it got wider. So now I'm going to be starting to work my way up. I'm going to go to sample size 10. I'm going to do sample size 10. So there's my 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which then gives me my mean. I'm going to do that over and over and over again. I expect my standard deviation to be smaller. All right, let's hit the 5 several times. All right, so we see as this is growing, this is becoming, it's definitely skinnier than it was before. And let me just speed up now. We see that it is now quite normal feeling. All right, and this time we have a standard deviation of 1.58. All right, let's move on up to 16. All right, so I can get my sample of 16. So from my parent population, I'm going to get a sample set of data, which is that second distribution, and from that we get one mean. And we do this over and over and over again. All right, so I'm pulling 5s at a time. And again, it feels a little bit skinnier, but I can speed this up and do this hundreds of thousands of times. All right, so now I'm at, I think I did that 1.5 million times. And our standard deviation is 1.25. That's a very nice number. All right, let's move up to 20. So my animation. All right, so I did it 20 times. And then from those 20, got one mean. All right, we can do this over and over and over again. I'm jumping by 5s. So we see it's making that unimodal look. So that we see that it feels somewhat unimodal. Let me jump up several times. All right, and we get a standard deviation of 1.12. And this applet only lets me go up to 25, and so we'll do this 25 times. All right, there's my big sample of 25, and from all 25 of those, I got one mean. I'm going to do that. I'm going to do this over and over and over again. So there we have it. I just did that 1.1 million times. And we have a very nice, scarily nice, standard deviation of 1.00. That's fascinating. All right, so there is actually a pretty interesting connection between these, and I'm going to highlight 2 of them. All right, let's take a look at this 16 and 1.25 and 25 and 1. So just a little challenge, just a little bit of a puzzle. I want to see if you can observe a relationship. I'll tell you that you're going to want to know the parent, the population standard deviation. So if you look at the top left corner, you should see it says SD equals 5. So the parent population is 5. And I want you to use that parent population of that parent standard deviation of 5 and my sample size. And I want you to try to see if you can figure out the one with the 16 and the 25. Take a second, fiddle around and see if you can see a relationship between that 5 and the 16 and 1.25, or 5 and 25 and 1. So I'll give you a second, pause the video, fiddle around, press play when you want to know the relationship. All right, welcome back. So here's the relationship. This says that the standard deviation of x bar, so notice that the subscript is x bar. That's because this blue distribution to the left is filled with x bars. So if I was to find the standard deviation of the distribution where all my items are x bars, well, I would start with this distribution on the top where all my data values are x's. So that's this sigma sub x, and I'm dividing it by the square root of n. So let's take a look at that 16. So my standard deviation is 5, and if I divide by square root of 16, this is the same thing as saying 5 divided by 4, because square root of 16 is 4, and 5/4 is 1.25. Now for the 25, 5 divided by my sample size of 25, square root of 25 is 5, 5 divided by 5 is 1. And if I do that for all 6 of these, from 2 up to 25, you'll see that our decimal approximation is either right on the money or pretty close to what we had. It might be a little bit off because, like I said, this is a simulated sampling distribution value. All right, so that's cool that my normal distribution, as my sample size grew, the standard deviation got smaller. That's something we've been talking about all year. Increase your sample size, you're going to decrease your variability, your increase your consistency. Also, I didn't make a big deal about it, but if you notice, the parent mean is 16, and on all of these, the sample mean is 16. That's a really big deal, but it's kind of obvious here. You saw that lining up right in the middle, just getting skinnier in that same spot. And then every single time we ended up with a normal distribution. This one's kind of boring, but let's move on to the uniform distribution. All right, so I'm going to change this to be sample size 2 and change this to the uniform distribution. So here's our uniform distribution. It's the same value all the way across. This data actually goes from 0 to 32. And I'm going to do the same thing. So we'll get our animated, so 1, 2, mean. Then here's the animated 1, 2, mean. For some reason, there's that bug that it's not showing anything other than the median right here, but it'll fix itself when I take more. 1, 2, mean. 1, 2, mean. 1, 2, mean. All right. So I want you to take a guess. So what you think will happen when I push the buttons really fast to actually fill out this picture a little bit better. Is it going to look like a rectangle, like a uniform distribution? Is it going to get skinnier? If it gets skinnier, is it going to still be a rectangle, or is it going to be different? All right, let's find out. All right, so I'm typing this 5 over and over again. Let's see what's happening. Well, it's becoming unimodal. That's nice. Also seems to be getting symmetrical. Has lots of little skinny skyscrapers. All right, I'm up to about 500. Let's speed this sucker up. And, so this is not normal. Let me fit the normal curve. It's definitely not normal. This is actually what we call the triangular distribution. It's this like perfect triangle. It just has a smooth slope going up and a smooth slope going down. Doesn't have that nice curvy nature that the normal distribution does. So you notice it doesn't fit quite as well. The mean is the same. That's nice. My standard deviation is bigger than the 2 was a second ago. It's at 6.73. All right, but not normal. Well, that's a first. Okay, well, let's move our sample size up to 5. And let's do the same thing. So I can get my sample 1, 2, 3, 4, 5 and get a mean. Let's speed this up. so I can get a bunch of 5 at a time. Get all these 5. Let's see what's happening as it's growing. All right, looks kind of maybe bimodal for a second, but I bet when I keep going, it'll fill itself out. All right, now this time we get a bit of a curve going in. So there's a bit of that curve action, and actually does a pretty good job. Actually feels quite normal. Right? And actually probably at this point with a uniform distribution with a sample size 5, it actually does a pretty good job of approximating a normal distribution. Here we have a standard deviation of 4.26. All right, so let's do these other ones a little bit faster. Sample size 10. So again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and mean. So that's what we're doing, sample size 10 and getting a mean from those. All right, so let's see what happens as this grows. I already have my normal model curve on there, and we see that it's trying its best to fit. Now let me speed it up and do 100,000s. And yeah, after about 1,000,000 times, does a pretty good job. It actually fits that normal model pretty well. We have a standard deviation of 3.01. All right, let's jump up to sample size 16. All right, so there's my sample size 16. After 1,000,000 of them, my standard deviation is 2.38. Let's jump up to sample size 20. And did a few 100,000 times. Oops, let's put that back. There we go, I'm up at 1,000,000. My gosh, it's being funny on me. All right, there we go. And we're at a standard deviation of 2.13. So notice as my standard deviation is as my sample size is increasing, my standard deviation is decreasing. Additionally, the means are lining up to the population mean, the parent mean, and my standard deviation is getting smaller. I can even test this. The standard deviation is, let me test it with the 25 because it'll be easier math. All right, let's move up to the 25. And then here's a few 100,000 of these. All right, there's 1,000,000 of those. And so its standard deviation is 1.90. All right, so just to test this, this is 9.52 divided by square root of 25, which is 9.52 divided by 5. All right, let me swap over to a calculator. All right, 9.52 divided by square root of 25, or just 5, is 1.904. And that does a pretty good job. So here it gets 1.9. Instead of 1.904, here's 1.90, which is what that rounds to. So yeah, that's pretty good. So notice, and if you test those, you can test those for all of these from 2 all the way up to 25, and all of those are going to be pretty close to that relationship that we observed with the normal. All right, last one that we're going to be keeping track of the standard deviations, and this is this skewed distribution. Now, skewed is not a named distribution. It is just this skewed distribution that this applet gives us. So that's not like a special distribution like uniform or normal. This is just this skewed distribution. All right, so let's go back to a standard deviation, sample size of 2. And so again, I'm pulling my sample, size 2, getting a mean. Pulling my sample, size 2, getting a mean. All right, we can speed this up. So what do we expect that's going to happen with the sample size 2? Well, already you should think, well, the standard deviation is going to be smaller because I should be dividing by square root of 2 so 6.22 divided by square root of 2. Is it going to look normal? Is it going to look just like what we saw a second ago, but just skinnier, like the parent at the top, but skinnier? All right, let me speed this up. And so notice we could definitely argue it is still skewed, but it's not as skewed. One, because the standard deviation got skinnier, but it isn't a perfect just scale down. It's not like you're in Word or Photoshop or something like that and you're making an image smaller. It's been changed. Notice it's much smoother at the top. It's pointier on our parent population. And our standard deviation here is 4.40. Which if I take 6.22 divided by square root of 2, I would get that 4.40. And also notably not normal. Here if I try to fit a normal curve, does not fit well at all. Let's move up to sample size 5. All right, let me just jump by 5s. Already much skinnier. But is it gonna be normal? Nope, not normal. Still a bit of a skew, but not as much as it was before. So now we're at 2.78, which would be if I take 6.22 divide by square root of 5, I would get about 2.78. All right, jump up to 10. And just jump to 100,000. And notice it's less skewed than it was before. And the normal model is getting better, but maybe not quite there. So we're at 1.97. Sample size 16. A few 100,000 of those. You could almost probably say that actually probably with this distribution, 16 probably works. 16 probably fits that normal approximation. And if I do 6.22 divided by 4, we'd get that about that 1.56. Just finishes out sample size 20. So that's a sample size of 20. There we go. 20 dots from our population. Then we get the mean, and we do that over and over again. And I get 1.39. And then lastly, sample size of 25. So again, just to be clear, I'm getting 25 dots from my parent population, 25 samples that I'm pulling, and then I get one mean, and then I do this process over and over and over again. There's my one mean, and I'll do this process over and over and over again. And so as that grows, it becomes gradually more and more normal. Remember, this applet does have a slight error. It's using the right edges of the histogram instead of the center. That's something that the authors of this are working on. So here we get a 1.25 for the standard deviation. So there's a lot of things happening here. So one also uses to point out, look at the blue numbers, the mean of 8.08. The mean is lined up, not in just a random location. The mean of the sampling distribution is centered on the mean of the parent population. Those means are the same. That's an X bar. Wherever the mu is on the top, that's the same center of this distribution on the bottom here. All right, so lots of things happened here. So one, we saw this relationship about our standard deviation. It's sigma over square root of n, the standard deviation of the population over the square root of n. We saw that the mean of our sampling distribution is centered at the mean of the parent population. But the big deal, the big reveal, and this is the thing that's called the central limit theorem, is that as our sample size increases, the shape of the sampling distribution of means. So here we're just talking about means. This also could apply if you're talking to sums. Sums are means, but nothing else. It is an approaching normality, and it gets a point that it's big enough that my sample size is big enough that the population is actually then considered normal. Now, with this particular applet, you can then draw our own. So I can just use my finger or my Apple Pencil. I can draw my own distributions. I'm going to draw a little bit more extreme one. That's one about like this. All right, so here's a pretty decent extreme distribution. And I'm going to drop this down to sample size 2. Curious if you want to pause the video and think for a second, what might a sample size of 2 look like with this distribution? What will a sample size of 2 look like with this sampling distribution? All right, let's find out. So there's my 1, 2, 1, 2, 1, 2. All right, let's speed it up a little bit. I have my fit normal turned on, and it's trying to make it fit normal, but I don't think it's going to happen. Let me speed this up some. So here I've done it about a million times. And yeah, it is not normal. It's actually very arguably trimodal. Well, why did that happen? Well, you saw it the first time when it did, just coincidence, and when it did the first 3 animations, you saw 1 in each of the 3 modes. So I got 2 from the right. So it's very likely that I might get both of my samples come from that right chunk, and that's that right mode. It's also very possible that both of my samples come from the left chunk, and that's the left mode. But then if I get 1 from the right and 1 from the left, then I'll get that one of those modes in the middle. So this gets this very trimodally shape, right? Let's move this up to sample size 5. So as my sample increases, we would expect, based upon what I said, that it should be becoming more and more normal-like, and it's becoming more normal, but it's not there yet. Feels very skyscraper, kind of like the that skyscraper city in Inception. Just lots of skyscrapers everywhere. Speed this up to millions of times, and yep, it's just this. It is this mound of skyscrapers that goes up, but we kind of have like what feels like about 6 different modes going on. Now, if I increase my sample size, here's a sample size of 10, about 2 million times. And there's these modes, there's now lots of possible modes, but they're starting to come together and smash on top of each other. They're not being very distinguishable from one another. But by the time I reach 16, this actually feels quite normal. Here's 20, and here's 25. So you see, even a crazy distribution like this, that with smaller smaller sample sizes, we were not getting normal. But here, we are getting normality, along with the mean of the population is lined up with the mean of the sample, along with the sample standard deviation. The standard deviation of the sampling distribution is the population standard deviation divided by square root of n. All that's happening every time. All right. Let me make a little bit more extreme skewed one. All right, that's a little bit more extreme than we saw a second ago. And let's do a sample size 2. And we can see with this, definitely not normal. Let's bump it up to 10. And it's starting to feel a lot more normal. Let's get up to 20. A lot better. The highest that this goes is 25. Now, in our textbook and within our course, there's a little bit of a magic number that we're going to look for, and that's 30. Now, 30 is not an absolute black and white gospel truth magic number, but in this course, we're going to say that if a distribution has a sample size that is at least 30 or more, that it is then big enough for us to apply the central limit theorem to say that the shape of the distribution is approximately normal. Now, there are some distributions that are so skewed that 30 is not enough, but maybe we only have to go up to 50, maybe even 100. But what the central limit theorem says is that there is a number that is big enough that that the distribution will approach normality. In this course, we're going to just say for all distributions that we will encounter, big enough is 30. All right, real fast, just a little bit of extra tidbit. I just want to point out that there are sampling distributions for things other than means. In this course, we're going to mainly be dealing with just the means. There's sampling distributions from means, medians, standard deviations, variances, mean absolute deviation, and ranges, and really any statistic ever, Q1s, Q3s, IQRs, any stat that you could ever think of or make up on your own, they have their own sampling distribution. But only the means or sums follow the central limit theorem. So just sort of kind of to prove this point, we're going to be looking at the range and the standard deviation. I have it set to sample size 2, and here's 100,000 of them in sample size 2, and you notice that neither of these are very normal. I can increase it up to sample size of 25 and do this 100,000, and they're still somewhat skewed or a little bit weird. All right, let me change this distribution up. And now let's go back to sample size 2 for both of those, and let's find the range. Well, that's interesting. There's a range in the green and standard deviation in the red. Yep, that's not normal, but it's just sample size 2. Let's jump up to sample size 25 and do the same thing. And the range is actually skewed to the left, right? Because there's this hard ceiling, and it's pretty common to get a 0 and a 32 at the same time. So that's why it's pretty easy for us to have a range like this. So it's actually skewed to the left. And it doesn't matter how many times I do it, it's not going to suddenly become normal. So only the means and the sums are going to can follow the central limit theorem. If I could do the same thing for medians and MADs or whatever, and again, central limit theorem is just reserved for means. All right, in the next video, we're going to be taking a look at some examples about applying the central limit theorem of means. So I'll see you in the next video.